Okay, let's get started. Today we are going to deal with the theory and the applications of recursive competitive equilibria or rational expectations equilibria or recursive macroeconomic equilibria. There are two consistent definitions available in the most important literature. One major source is the Ljungqvist Sargent textbook, and the other important source is our textbook, the Stokey-Lucas textbook. They offer the same definition, which you can find. Let me summarize the main points, the major points of this one and only definition. There is a representative agent, or there are representative agents. They form rational expectations regarding the dynamics of some macroeconomic variable, one or more macroeconomic variables. They think there is an aggregate law of motion that governs the dynamics of these macroeconomic variables. On the basis of these expectations, they form a policy function. So they optimize on the basis of this perceived aggregate law, and as a result, they can behave optimally under any circumstance. And in equilibrium, this perceived aggregate law and the actual aggregate law will be the same. In this lecture, we will go over some exercises that mainly come from the Ljungqvist Sargent book. They are really exciting, I promise. And we will, most importantly, we will take a twofold approach. So first, we will solve the problems in the social planner approach, when there is a social planner that aims to maximize the utility of all the agents. This is the aggregate solution, and then we are going to solve the problems in a disaggregate fashion with rational expectations, and we will say that both solutions are the same. Okay, first we will solve the problems on paper with pencil, and then we will work out the solutions in MATLAB. So this is what we are going to do in turn. Okay, let's start with a problem from the Ljungqvist Sargent book. This is the model in section 7.4. Okay, here we only translate the problem into the language of the optimal linear regulator. Okay, let's take the social planner approach. The objective function of the social planner is to maximize. This is the problem of the social planner, to maximize the value of this objective function. This is a stochastic problem. Capital NT is the labor force in period T, which is affected by prior schooling decisions of the household. So NT is the decision variable. This is the control variable, new entrance into the schooling system. We have two constraints. one equation describes the dynamics of the stochastic shock in this system, and the other equation describes the dynamics of the labor force, which stands under the influence of the schooling decisions of the household. This is an IID shock with zero mean. Okay, so it takes 4 periods for the new entrants to the schooling system to become a full-fledged labor force. Because of the time-consuming character of the education system, we have a long state vector. Okay, this is the state vector. So let's start working out the optimal linear regulator representation. So we have, we have this vector as the state vector next period. This is the state vector in period t plus 1. Here we are going to have a huge matrix SA. This is the easy part, the state vector in T. All right, this is xt. Here comes vector b that incorporates the decision of the household in period t. Yep, and there is only one thing to do to incorporate the effect of the stochastic shock to the system. Okay, all right, this is C, and this is the stochastic noise. It's no big deal. It's easy to realize that the length of the state vector doesn't complicate things too much. Okay, hopefully it is. All right, so the first equation is done, and we need 2 more matrices from the objective function. Matrix R is on the state vector. Yep, no. 1 over 2 minus f2 over 2, f1 over 2. Here we have zeros in 3 columns. Nope. This is 0. And this is f1 over 2, 0, 0, 0, f0. And q is simply minus d over 2. So we have all the 4 matrices to put into the optimal linear regulator. From the optimal linear regulator, we will have an f function, a function f, that describes the optimal response of the social planner to the state, and it implies a first order difference equation in terms of the state vector. First order difference matrix difference equation that describes the dynamics of the state. Okay, and we will see in the later exercises, we will see that the dynamics of NT and capital NT, as found by the social planner, both dynamics are going to be optimal in the rational expectations equilibrium of the disaggregated model. So we will solve this problem in a simplified version, and we will solve this problem in MATLAB to see, and we will solve other exercises, further exercises too, to see what it takes to formalize a problem in rational expectations equilibrium. Let's go on with a simplified version of the same model. I'd like to show you how to identify the objective function of the social planner on the basis of the objective functions of the agents who are involved in the model. We have a firm and we have a household, so the social planner wants to maximize the objective functions of both agents. So let's see them in turn. The firm's problem. The firm's problem, it wants to maximize its profit. This is a profit flow, a discounted profit flow. This is a production function with one input, which is labor force. This is, yes, this is a production function with one input. I'm just double checking. And the firm pays a salary to the household. The household's problem is similar. It wants to maximize its own profit which is the difference between income and a cost, quadratic, a strictly convex cost function which is related to education. Okay, so NT is labor force in T, and this is capital T, and NT is the control of the household regarding schooling, new entrance to the schooling system, and education takes 1 period. So we can suppose that the dynamics of the labor force is affected by the decision of the household through this equation. So NT is the decision variable of the household, and the social planner wants to find an optimal path for the labor force and a related optimal path for the new entrance into the schooling system. So the social planner's problem is simply the sum of these objective functions. Here, first, I'd like to show you the full version, and then we can simplify it very easily. So this is the objective function of the firm. You can easily realize that this is a deterministic version. And here comes, so this is the objective function of the firm, and this is the objective function of the household. All right, so this is the household, and it's easy to realize that this guy and this guy cancel each other, so we can simplify the social planner's problem. Okay. All right. So this is the social planner's objective function. By maximizing this objective function, it can maximize the utility of both of the agents. So we only need to solve the social planner's problem, and the optimal solution to the social planner's problem will solve the problem, the optimization problems of both agents. All right, so first of all, let's translate the problem into the language of the optimal linear regulator. It is still true, of course. I was just thinking for a split second. This is assumed to be a constraint. So here comes the first matrix from the objective function of the social planner. Okay, because the state vector is really simple, that's all we need. Okay, this is the state vector, and this is the control variable, the new entrance to the schooling system. So we have R and we have Q minus D over 2. And we need the equation as a second step. We need this equation, which is going to be an easy feat. Here we go. Okay. And in the language of the optimal linear regulator, this is matrix A, this is the state vector in period t, this is B, and this is ut. So we are done. Okay, here we assume that D is strictly positive in order that matrix Q, it is a matrix, it is a 1-1 matrix, it is supposed to be negative definite. And we must be careful when choosing values for F0, F1 and F2 because R is also supposed to be negative definite. It's easy to solve in MATLAB when we have the appropriate parameters, and we will solve this version of the problem in MATLAB. But first, before doing anything in MATLAB, let's have a look at the disaggregate case. How to interpret, how to set up the disaggregate case. The household knows, so let's start with the expectations and the knowledge. The household knows that future wages are dependent on future labor force through the wage equation, which comes from the first order condition of the firm. And given the fact that the labor force, the dynamics of the labor force is affected by the decisions of the household, and given the fact that future wage is dependent on future labor force, the household must forecast the future dynamics of the labor force. So the household sets up a forecast function or something like that. So we are in period t, and the household wants to plan an optimal path for the new entrance to the schooling system, because it knows that future labor force is always affected by its own decisions. And here comes the recursive part of the problem. So here we are modeling how the household is trying to forecast the future path of the labor force in order to forecast future wages, because future wages are dependent upon the future path of the labor force. Okay, so we have two forecasts. And please note that both are dependent on the decision of the household it makes in period t. Let's work out a few more periods. It takes time, but it's a useful practice if you want to be really good at such recursive structures. They are so beautiful. I really love them. So, and this is the third period, as the household predicts labor force in period T+3. Oh geez. So we have the third prediction, and we can continue. It's easy to generalize. The next case is obviously, and please note before moving on, please note that period T decision is also here. And here no 2 n t+2 and n t+3 n t+1 t+2 t+3. And in general, so we have a pattern we can generalize. So following this pattern, we can forecast the labor force in any future period ahead of t. And please note, nt is here. So in sum, we can say that the household knows that its decision in period t, actually in any period, affects the dynamics of the labor force in any future period. So it's a complicated problem. Okay, and dj minus 2 and dj minus 1. Okay, all right, so let's get back to the optimization problem of the household, and let's use these predictions. So once again, the household wants to maximize this profit flow or net income flow, whatever. Okay, and we need to find the first order condition regarding its decision in period t. So this is what we are interested in. So let's expand this objective function. It takes some recursion again, but no problem, it's really nice. It goes to infinity, it's an infinite sum, and finally this term closes the sequence. Okay, this is given in t, and hence it's not affected by nt, the decision variable. Please note that it is affected by the period t decision. It is also affected by the period t decision. Okay. So this is what we need. In sum, we can say we are trying to formalize this problem in more and more briefly. I'm just summarizing. And I'm trying to focus only what really matters. Okay, and now we are derivating this function with respect to the decision variable. Please remember, please note, we are interested in finding the first order condition for the decision in period t, and this is what we have. It's going to look like a proper first order condition. And we can rewrite the whole stuff okay. And finally, this is what we have. Hopefully it's correct. Because, yep, it's important to incorporate the running index. Okay, and from this, we have an interesting thing. Which is a supply function of the household as a function of the future wages in any future period. Okay, so the optimal decision in period t is dependent upon the wages in the subsequent periods. All right, the household, here the households assumes that this equation works. So this is the equation that describes wage dynamics as a function of the dynamics of the labor force. And you may realize that this function comes from the first order condition of the firm. There is another assumption. The household assumes that there is an aggregate equation that describes the dynamics, an exogenous aggregate equation that describes the dynamics of the labor force. In other form, the household believes that there is a perceived law of motion. So there is an exogenous perceived law of motion that is accepted by the household. Any perceived law of motion, in other words, any parameters H0 and H1 imply dynamics, a path for the optimal decision of the household according to the supply function of the household. And this dynamics, any dynamics of the optimal decision implied by the perceived law of motion implies a path for capital NT, the labor force. But there is a problem here. The path for capital NT as implied by the optimal decision of the household and the path of capital NT as implied by the perceived law of motion, they are supposed to be identical under rational expectations equilibrium. So the household, it means that the household expects in rational expectations equilibrium what actually works in reality thanks to its optimizing behavior. However, there is only one pair H0 and H1 that implies itself through the optimizing behavior of the household. This is the social planner's solution to the optimization problem. Okay, so the path for the labor force found by the social planner taken as a perceived law of motion implies itself through the optimizing behavior of the household. So the path for the labor force that we get as a solution in the disaggregated version of the problem, it turns out to be the same in rational expectations equilibrium. It turns out to be the same as found the social planner in the aggregated version of the problem. In later exercises, we will see how it works. Let's try to solve the simplified version of the Ljungqvist-Sargent human capital accumulation model. It's going to be an easy feat, I promise. Let's start a new live script and let's start with the parameters. We need 1, 2, 3, 4, 5, 6 parameters. This is the discount factor. Let's choose the usual value. This is the cost parameter, which, no, it's not that. This is the parameter from the law of motion for the labor force. This is the cost parameter, and here comes the parameters from the reproduction function of the firm. We need to make sure that matrix R is negative definite. It's easy to check, you will see, because we will see, because we are going on with the matrices. So this is matrix A that describes the dynamics of the exogenous part of the dynamics of the state. This is the vector that incorporates the effects of the decisions of the household. This is matrix R, which is supposed to be negative definite. This is F2 over 2 minus F2 over 2, F1 over 2. This is symmetric, so the second row starts with F1 over 2 and finally F0. Q is minus D over 2, and we need a technical vector which I will explain to you in turn. But before doing anything, let's run what we have and let's check if matrix R is negative definite. We can check it if minus R is positive definite, and it is positive definite if the eigenvalues are strictly positive, and we can see that the eigenvalues are strictly positive. So minus R has positive eigenvalues, so R is a negative definite, so we are good. We are going to solve the problem. As you may remember, we wrote an own Riccati equation solver, a short algorithm, in TA session 4, as far as I remember. But now let's try to use the Riccati solver, Riccati equation solver, by the Ljungqvist and Sargent book. So as you may know, you can download many MATLAB scripts and programs, and these programs include a function which solves the Riccati equations we need. We can open the program. I'd like to show you one thing which you are supposed to bear in mind. So this is the program, and we have written in green, we have a short user guide. These are the arguments of the program. You can see a matrix W, and we will see why it is needed. It is needed when there is a cross product between the state and the control, and given the fact that we have no cross product, we can set W to 0. Here, if there are no cross products, W is supposed to set to 0. So this is the reason why we use this technical vector. And there is one more thing I'd like to show you. Please have a look at the labels, the names of the matrices in the objective function. Q and R are reversed. So what we label as Q, it is R in the language of this program, so we must be careful to switch the order of Q and R when we are giving the inputs to this application. So it's easy, it's an easy thing. So but we need to be careful. A, B, not QR, but RQ. Okay, and W. And let's calculate the optimal law of motion. So by running this program, we can see that this is the law of motion to the optimal path for the labor force chosen by the social planner. And as you may remember, what we have already covered in this session. This is the only perceived law of motion that implies itself through the optimizing behavior of the household in the desegregated version of the problem. So we can expect that this is the only, once again, this is the only perceived law of motion to which the household responds in a way that implies a law of motion for the labor force that is consistent with this perceived law of motion, that is identical to this perceived law of motion. This was the point. In the later sections of this session, we will see how to find the rational expectations equilibrium in a simple model. This is exercise 7.1 from the Ljungqvist Sargent book. This problem is about a competitive firm. A competitive firm wants to maximize its profit flow where the profit flow is the difference, is interpreted, is understood as the difference between revenues and costs. And please note that the profit is fraught, or production is fraught, with a quadratic cost function. So PT is product price in period T, and YT is output. All right. So it is given. This is the starting value for the path of the output. It is given. Okay. The firm knows. The firm forms expectations. The firm thinks that price is determined by this demand function. So this is a function, price is a function of output. So it is known, and the firm thinks that the dynamics of the output, GDP, whatever, is governed by this first order difference equation. This is a belief function or expectation. Okay, so there is something the firm knows, and there is something that the firm believes. All right, let's start with the Bellman equation. of the firm. It's no big deal because it's easy to realize that on the basis of the objective function, we have the one period return function. First, let's identify the state, its own output, and the aggregate output. And the decision or control variable is the change in output. It's easier to form the problem in this way. So the Bellman equation is built on the maximization with respect to output next period Okay, so this is the Bellman equation, but we need to bear in mind the fact that product price is supposed to be governed by an exogenous equation, a function. So the Bellman equation can be rewritten with these parameters. Okay, this is the Bellman equation where the firm believes that this process describes the dynamics of the exogenous state. Let's translate the whole problem into the language of the optimal linear regulator. The state must include both variables and perhaps other variables. So we have determined the control variable and the state for the firm. So let's try to formalize everything in the language of the optimal linear regulator. This is going to be matrix A that contains the belief parameters. This is A. Okay. It's supposed to be an NN matrix, so we need it to expand the state vector into a 3-1 vector. Oh geez. I'm confusing everything. Okay, so this is B, and this is the decision, the control variable in period T. This is okay. This seems to be okay to me. Okay, and we need, so we have matrix A, vector B, and we need to identify on the basis of the objective function matrix R and matrix Q, which is not difficult. And Q is minus D over 2. Okay, it can be written as a 1-1 matrix. I think we are fine. And from the optimal linear regulator, we will have an f, a function f, that implies the response of the firm to the state, the optimal response of the firm to the state. This is equation 1.45 from Sargent's textbook. Okay, and in representativity, the firm is representative, so what the firm produces is the GDP itself, and in a split second we will see how it changes the model. So we will see that there is only one perceived aggregate law of motion that is consistent with itself. So the firm, through the optimal linear regulator, the firm responds to any state, and the optimizing behavior of the firm implies, through the fact that the firm is representative, an actual law of motion. But so we have a perceived law of motion and an actual law of motion as implied by the perceived law of motion. But under rational expectations equilibrium, the perceived law of motion and the actual law of motion must be the same. So this is what we are going to do in turn. Let's go on with exercise 7.3, the social planner problem of the social planner formulation of the same problem. The social planner wants to maximize this sum, discounted sum, where st is a function of this period's and next period's output, this is the demand function, and this is the area under the demand function. So this is the difference of the area under the demand function and the expenditures of the household. This is the takings of the firm, and these are the costs. Okay, the same convex cost function. So this is what the social planner wants to maximize. It's easy to realize that these two items cancel each other. So what remains is this term, which is still the sum of the consumer surplus and the producer surplus. Okay, so first, before going on, let's calculate the integral. It's no big deal. This is really, really simple. It's the bonus. Okay, and this is the one period return function for the social planner. So the Bellman equation for the not the one period return function, the first half of the one period return function. So all in all, the Bellman equation for the social planner is the following equation. The costs and the value function next period. Okay, so this is the Bellman equation, and let's try to translate the problem into the language of the optimal linear regulator. Just like previously, let's set the control as the difference, the change in aggregate output. So the objective function for the social planner then where this difference is the control. All right. The state vector is really simple. Okay. It's easy to realize that matrix Q is this 1, 1 matrix, or is also simple. Okay, so we have two matrices and we need another equation that summarizes the impact of the control on the dynamics of the state. So this is the state vector. All right. So So this is x t plus 1. This is u, this is b, this is xt, and this is this simple. All right. So we have all the matrices that we need to have the problem written in the language of the optimal linear regulator. So let's have a look at these problems in MATLAB. We don't need to spend too much time solving this problem. I have already written the script. It's very simple. This is the script for exercise 7.1. I changed the exercise in one respect. Later, in a minute actually, you will see that these parameters are the rational expectations equilibrium parameters. Soon we will see how to get them. The point is under this belief function, the firm follows this policy function. So these are the parameters in f, the policy vector, and this is the script for exercise 7.3. This is the problem for the social planner, and you can see that we have the same parameters in the policy as the optimum policy. Don't get frustrated by the dimensions of the policy vector. Here the state vector, as we have just seen, the state vector is a 2-1 vector. In the case of the firm, we had a 3-1 vector, so this is the reason for the difference in dimensions. It's no problem, it's okay. And you can see that the social planner found the same parameters for the optimum path of output. And in the next part of this exercise, which is the final part of the exercises for the day, we will see why it is that these parameters here are the so-called rational equilibrium parameters. We will write a short code for finding these equilibrium parameters, and I will show you how to do. In exercise 7.2, we face a very interesting aspect of these problems, the rational expectations aspect of these problems. We realize that to any age 0 and age 1 pair, the belief parameters, we have an optimal policy f from the function that describes the optimum policy of the firm as a response to the state. So in this exercise, we have some belief parameters, some pairs, age 0 and age 1 pairs, and we are supposed to decide which of them is consistent with rational expectations. To this pair, where age 0 is 95.8 0.1874, and H1 is 0.952459. So to these belief parameters, we have the following policy function. And the textbook says, the Ljungqvist Sargent book says, that this is the belief function which is only consistent with rational expectations, and we need to see why. Okay, so it is a fact that to these parameters we have this policy function, and if we use this representation, then we will have on the basis of this policy function that this function describes the optimal behavior of the firm as a response to the aggregate state. So please note that this is the decision variable of the representative firm, and this is the aggregate variable, capital Y. Thanks to representativity, given that n is 1, so we have only one representative firm on the market, which is a price taker, we can write the same equation in this form. And if we simplify the equation, we will have this function, which might seem familiar to you because these are the belief parameters we used. So in rational expectations, on the rational expectations, the firm forms some expectations regarding H0 and H1. This pair of belief parameters implies an optimum policy F that, thanks to representativity, leads to an actual H0 and H1, and these two pairs must be in line. They must be the same. This is the part of the definition of rational expectations equilibrium, that that under rational expectations in equilibrium, the perceived aggregate law of motion and the actual law of motion must be the same. So in the final part of this session, we will write a short MATLAB code to find the rational expectations equilibrium parameters in this exercise. All right, let's close this session, today's session, with this script to find the rational expectations equilibrium in exercise 7.2. So let's go. First, let's start with the parameters. We have 4. The discount factor is 0.95. A0 is 100. It is still 100. All of them remain. the same 0.05, and the parameter in the cost function is 10. Okay, let's take a section break and let's start setting up the iterative algorithm to find rational expectations equilibrium. The idea is simple. To any to any perceived law of motion H, the optimum linear regulator as a mapping implies an actual law of motion. So to any belief function, perceived aggregate law of motion, the optimal linear regulator, the optimization problem, the solving of the optimization problem implies an actual law of motion. So this is the basic idea under the iterative algorithm. And there is an interesting fact, and this is a mapping. It has a fixed point. So there is one perceived belief law of motion that implies itself as an actual law of motion. So our iteration will be based on this idea. We will make an initial guess as a perceived law of motion. We will calculate in each round of the iteration, we will calculate an actual law of motion, and we will compare the belief function and the actual law of motion. And if a perceived law of motion implies itself as an actual law of motion, then we can stop. So this is what we are going to do. So this is an iteration process. So let's establish the maximum number of iterations. The maximum number of iterations. As we need to compare the belief function and the belief law of motion and the actual law of motion, the easiest way to do is to collect these perceived and implied functions in a huge matrix, because working with a matrix is easy. We can easily compare the rows, the consecutive rows of such a matrix. So here we are assigning the matrix of belief aggregate. Aggregate belief parameters. Okay, NH. Okay, we need to pay attention to a stopping criterion. So as I have just mentioned, we are going to compare the rows of this matrix, the consecutive rows of this matrix, the laws of motion. So we need a vector to collect the differences. Okay, so here we are assigning the vector for difference of laws of motion. Okay, we need a threshold. when the difference falls under this threshold, our algorithm is supposed to stop. Okay, D, alright, E is the tolerance. Okay, and here we are giving the first row in this huge matrix this is an initial guess. It can be any number. I've set it 1 to 1 1. Initial guess for age 0 and age 1. Okay. Initial guess for age 0 and age 1. And now N, H, D, E, and the first row. Okay. And now we are ready to set up the for loop. We can start the iteration with 2 because we have already had the first row as an initial guess, the first row of matrix age. The for loop, okay, and here we are giving the matrices on the basis of which our algorithm is going to work. Matrix A is crucial because, as you remember, its second row contains the belief parameters. Okay, so here we are indexing into that matrix to get the belief parameters. In the first row of the matrix we have an initial guess, and in the first round of iteration we will use this initial guess, and in each round we will update this matrix. 0, 0, 1, 1, 0, 0, 0, age I minus 1, 2, I minus 1, 1, 0, 0, 1. Okay, it sounds like a poem. Vector B is simple. 1, 0, 0. Okay, or zero minus A1 over 2, A0 over 2, so 0 minus A1 over 2, A0 over 2, second row minus A1 over 2, 0, 0, and A0 over 2, 0, 0. Okay, minus A1 over 2, 0, 0, A0 over 2, 0, 0. We are done. Q. It's not necessary to give it as a 1, 1 matrix, it's just by convention. Minus 0.5 times D, and we have this technical vector W to make the Riccati equation solver work properly. There is no cross product, so this is the reason why we need this technical vector. Okay, and now we are ready up to a point, so we can solve the problem to the given belief function R, Q, and W. So in each round we will solve the problem calculating f in this equation. So the algorithm, the iteration is simple. We will have a belief function, a perceived law of motion. On this basis, we will have an actual law of motion, and we will check if the perceived law of motion implies itself. If not, we will use the new law of motion as a belief law of motion, and we will solve the problem with this belief function. We will go on until we find a belief, a perceived law of motion that implies each other, which implies itself as an actual law of motion. Okay, so we solve the problem for the policy function, and most importantly, we are supposed to update the matrix H with the new actual law of motion, which we can use in the next round of iteration as a perceived law of motion. This is the simple calculation we performed in the previous step at the blackboard. So this is the way how we make the firm representative. Okay, so the policy function implies a behavior on the part of the firm, and by making the firm representative, we will have this behavior as an actual law of motion, and this is what we are doing now in this calculation. Okay, so hi 1 2 minus 1 times f3 1 minus f2. So here we are updating the matrix of aggregate belief parameters. All right. Okay. There is only one thing to do to complete the stopping criterion. As I mentioned, we are comparing the consecutive rows of the matrix H in which we collect the laws of motion. So here we are comparing the consecutive rows of this matrix. So we want to find the difference between two rows, and we need the absolute value, and we need the largest of the two, because I'm saying 2 because the law of motion has two parameters. So we compare the parameters h0 to h0, h1 to h1. We take them in absolute value, and we focus on the largest of the two. And we want to go on with the algorithm until this difference, the highest of the differences, falls under this threshold, the tolerance threshold. Okay, h1i 1 2, h1 minus 1 1 2. Okay, calculating, no, creating the stopping criterion. Okay, hopefully it's going to work. Okay, and here we order MATLAB to stop the algorithm when the difference falls under the threshold. Break, we close this order and we close the for loop. And I think we are ready to run the script. And while it is running, let me summarize. So there is only one policy among the optimum policies which is consistent with the perceived aggregate law of motion. To each perceived law of motion there is an optimum policy, but we need consistency because of the fact that the firm is representative, so n is 1. The only one consistent policy is optimal policy that implies an aggregate law of motion, an actual aggregate law of motion, which is exactly the same aggregate law of motion which was found by the social planner to optimize the utility, to maximize the utility for the firm and the household. So it's running, the application is running, the script is running, and what we are expecting is the same policy function f which we found under exercise 7.2 in the Ljungqvist Sargent book. And if you have a look at the result, it's great. It's the same policy function. So this is the policy which is consistent with rational expectations. This is the policy which implies, let me summarize again, this is the policy which implies an actual aggregate law of motion which is the same as the belief or perceived aggregate law of motion on the basis of which the firm formed rational expectations. So we have an iterative algorithm to find rational expectations equilibrium in exercise 7.123. Okay, that's all for the day. As a final step, let's have a quick look at the disaggregated solution of the households problem. Just a reminder, this is the objective function of the household. The household wants to maximize its profit flow, which has an income component and the cost component. The cost function is quadratic, and the wage component, the income component, has two parts. First, the household knows that wage is determined by this equation, which is based on the first order condition of the firm. So this is a demand for labor force. On the basis of wage, you can see higher labor force, lower wage. So this is a demand for an inverse demand function for labor force based on the first order condition of the firm. The household takes this equation for granted. And most importantly, you can realize that there is a new variable in this equation. This variable is the aggregate labor force, with respect to which the household forms some expectations, believing that labor force aggregate or market level labor force dynamics follows this equation. This is the perceived law of motion, on the basis of which the household forms rational expectations, and on the basis of which the household wants to maximize its profit flow. And we have a third equation. The household, on this ground, the household wants to optimize its labor supply with the decision variable, period t decision variable, which is schooling in period t. Okay, so these are the three equations with which we are supposed to work. We have a new state vector that contains this new aggregate variable, the labor force, which is the endogenous state, and we have a technical component in the state vector. So on this basis, we can rewrite the household's problem just to be more specific. This is the same problem, but we will use the demand function. So you can realize that this is wage in period t, governed by this exogenous law of motion. Here comes the endogenous state, and this is the cost component. Okay, and we can rewrite the same equation again to get ready to translate the problem into the optimal linear regulator framework. That's all. That's all. So now we are ready to put the whole stuff into the framework of the optimal linear regulator. No surprise, this is matrix Q. This is a 1-1 matrix. R is not difficult at all. Please note that both Q and R are supposed to be negative definite or semi-definite matrices, so we should be careful when choosing the parameters. Okay, this is matrix R. This is symmetric, and by carefully choosing the parameters f1 and f2, we can make it a negative definite matrix. And let's find matrix A and B. This is the state in t plus 1. This is supposed to be matrix A. Okay, this is implied n and 1. Zero, 1, 0. Okay. Later. Let's see the structure before doing anything. This is B and the control. Okay, so n, it is true that this is the state and schooling is the control variable. Here we have the expectations parameters. Okay, because you can see this structure in this matrix difference equation implies that our equation holds, so it's all right, it's okay. In the second row we have delta, because you can see this is the endogenous state, and it helps to realize that it is supposed to be 1, and finally 0, 0, 1, 0, 0, and we are ready. So now we have translated the problem into the framework of the optimal linear regulator, and in broad terms, the problem, the household problem, is the household wants to optimize its own labor supply on the basis of an exogenous law of motion with respect to wage dynamics, and the solution is a policy function in the form of a vector, a 3, 1, 1, 3, sorry. This is a 1, 3 matrix. And in the next step, so after solving the problem, the optimization problem of the household, we will make it a representative household, and we will find that the law of motion found by the social planner is the same as the solution of the in the disaggregated problem. You can easily check it in MATLAB if you use age 0 and age 1 the law of motion of the social planner. You will realize that it is a law of motion that implies itself in the rational expectations equilibrium.